Start streaming. There we go. Let's do a new background. That seems a little... There we go. Ah, a dead kitten. That's Schrodinger's cat. That is how you'd express mathematically its odds of being dead or alive. It's also... Schrodinger's cat wasn't made as an example of how to understand it, by the way. It was made as an example, someone made that as an example to show how stupid it was. Like, this is so stupid that if you had a cat in that position, this is what you're saying. And the quantum chemists were like, yep, that's exactly what we're saying. We're going to take your example and use that to teach people how it works. Now, you might think that Schrodinger's cat only applies to, say, very small molecules. Is it there? Is it not there? For those of you who haven't heard of Schrodinger's cat, essentially there's a cat in a box, and there are a variety of ways to die in that box. A radioactive sample can set out a little piece of radioactivity that would set off a trap that would kill the cat. So you don't know if the cat is dead or alive. Now, in real life, the cat is either dead or alive. But in quantum chemistry, in particles, it exists in a quasi-state where it is both dead and alive at the same time. We know these states exist because a single photon in light has the ability to go down two different paths at the same time. So they can exist in quasi-states, provided the universe is not observing them. Observing does not mean an intelligent mind. It just means something else like hitting it.
Some quantum physics actually be dead right?
Yeah. Now, that being said, it only applies to particles. We've managed to get it to work with particles as large as viruses, which are like a thing. A whole thing. And so that is starting, can you keep things in a quantum state larger and larger? Sorry, I'm getting distracted now. I should be bringing up our notes.
No, we can talk about the
Well, quantum chemistry is pretty cool. They also managed to recently teleport an object. Where they took an atom and measured all of its properties and then recreated those properties on another atom of the same type. That's not transportations, but is there a difference? If you walk into a Star Trek transporter and it completely scans you, but in the process completely destroys you, but then recreates your body down to the atom somewhere else, that's kind of like transportation.
Wouldn't you be the same person, though?
Yeah, that's a good question. That's the ship of Theseus problem.
They should test it.
Yeah, we should test out and we just destroy and rebuild it.
That's why some characters in Star Trek refuse to use the transporters, because they don't believe that they're the same person when you come out the other end.
They should just use people on death
We
row.
should watch Star Trek.
Okay, if your solution to an ethical problem is to hurt more people, you're probably, although, for some ethicists, that's okay. It's called utilitarianism. Okay, we were up to, we did that. I think we did this. We just didn't write it down, correct? Didn't I ask you to do this, like, in class?
We did that.
Or did this just not save? We were past this, weren't we?
No.
No? What?
No, we didn't do that. We didn't do this part.
We ended before that.
So we ended...
We ended on... Yeah.
Did we do it? We did that one.
Yeah.
Wait, can you go back to that?
That one? No, it's live streamed. It's live streamed. To the person who wasn't here, right? So I'm going to open up a guest.
I know where it is. I just didn't want to have to go search for it.
Oh, okay.
It was right there.
Yeah, there you go. Okay, you've got 30 seconds. Calculate the rate of B and C from that rate right there. So this is A. I will take attendance while you're doing that, and then ask two random people to give me how they calculated that. Class Dojo. We are. Andrew.
Hi.
Ashley. No. No, Ashley. Davis. You have to say here, present. Davis. No, Davis. Druvy. Ella. Etienne. Gleb. Johan. Josh. Katie. Lavina. Max.
Here.
Nathan.
Yep.
Nicholas.
Yep.
Sam.
Yeah.
Samuel.
Yep.
Taz.
Yep.
Tatum. Where's Dave?
She dropped the class.
Wounded. And Theo.
I think David also dropped class.
Hey, maybe. I'll check with the official. This is my rough attendance. And then I transfer it afterwards when we have a moment.
You know, if it's CR be
Explain how to do this.
a good way.
Oh, yeah. But you weren't here. So first I'll probably ask you, and then you'll be confused, and I'll give you a lot of hints.
Is CR and PR a good way to represent like production rate and consumption?
CR? What?
Like, are the like if I was to use CR to represent consumption rate, would that be a good way to present?
Oh, I would do it. I would just rate of A is equal to 2.10 times 10 to the minus
Well, would
5.
you understand what I'm saying if I say CR?
Probably not. It's a non-standard abbreviation. But if you define it somewhere, that's fine. There, that's a better question. First up, explain to me how you got the rate of B from A is Katie. Yeah, you're the first name it picked.
Wait, the rate of A?
Yeah,
Well, can you do like the multiply by where you're going, divide by?
that sounds like a great idea.
It's the same as stoic?
Pardon?
It's the same as stoic?
It's exactly the same as Stoic.
Okay.
See, that's why it asked you. It knew that you knew what you were doing. So what would you multiply it by if you're at A and you're going to B?
1.
No, divide by 2.
Divide by 2 and divide by
Yeah. So we multiply by 1B over 2A. And that way we're converting it. And what do you get? Gentlemen.
0.5B.
Pardon?
0.5B.
Oh, no, I'm waiting for Katie. It was Katie's question.
Sorry, what was it?
Well, what is the actual numerical answer?
It's 2.10 divided
Oh, you're just saying what it was.
over 2.
Yeah, no, I've got that part.
So it's 1.6.
Haha.
1.6 has a
1.60?
60. Or it's, sorry. I honestly don't remember.
Okay, okay.
Oh,
Take,
1.05.
Right.
times 10 to the negative 5.
I was going to say, take it slow. What's half of 2? 1. And what is half of 0.10? 0.05.
Why is rate A 10 to the power?
Isn't it
negative 5?
Yeah, is it negative 5?
That is negative 5. There's
It
just,
says 5.
That does not look like a negative 5.
well, it was negative 5. Lies.
In rate
There's
A?
no negative there.
There's no negative.
There's a negative right there.
No, but I'm saying for rate A.
No, we're at
You
the
wrote
bottom of the thing.
10.10 times.
That
Oh.
is negative 5. Yeah. It probably just overlapped. Okay, random person for a number for C is Nick Meyer.
2.10 times 10 to the negative 5 times by 3 divided by 2.
And what'd you get?
3.15 times 10 to the negative 5.
Moles per second. 3 sig figs, 3 sig figs. Excellent. Okay.
Do we have to specify if it's being consumed or produced?
If it asks you, and sometimes when you answer questions in English, then that will do it. You can also get negatives. Negatives imply consumed, and positives imply produced,
No, but
unless
let's
you say it differently.
It's a positive 1.05.
No, because I just assume it's B, so it's going to be consumed.
No, I understand that, but would
Yep.
you then say negative 1.05?
You can. I'll know what you mean. But generally, you'll find we don't have to.
So it doesn't matter.
It doesn't matter.
Wait, I'll help you.
Yes?
Can you write 10 to the negative 5? Like, is that a real number? Or, like, is it, like, or do you write, like, 1 over 5? Like, can you
2.10 times 10 to the minus 5. What's your question? That's scientific notation. It's not an inverse. Necessarily. Well, in a way, it is. Remember, this means this goes 1, 2, 3, 4, 5, and that actually means that it's scientific notation. Yeah. Okay. I'm going to bring out some demos. Before I do that, what are some ways, if you're observing a reaction, that we can measure how fast it is going?
Time.
So, we will measure in time. What are we measuring?
How fast it's going.
Yeah, but how will we know how fast it's going? There and then there, yes? So temperature, if you have a reaction that gives off heat or takes in heat, if it's getting colder or hotter. So we have a temperature change. If I'm asking you, this may, why is that written there? Is that on your notes?
That's the link for first page.
Yeah. Some of what's down there may actually give you some hints. How else would we do it? Yes.
The weight before and after.
Wait before and after. So we can do the change in mass. This only works for some reactions. What would the reaction have to give off for a mass change to occur? Gas. So gas evolves. I've used Alka-Seltzer bubbles. That's a demo I may do. Yes.
Color.
Color. Nicely done. If you spell color without a U, that's okay. We accept ESL students as well, but try and get used to the proper English spelling. Now we measure that with a spectrophotometer, so fancy word there as well. So we got color, we got temperature. We're missing at least one. This is the one if you you could do a mass change, but you have a sealed container.
Pressure.
Pressure. And for all of these, I am going to belabor the point. If we are measuring a color change, then the reaction, I don't want to write reaction every time. Then the reaction rate is the change in the color intensity over the change in time. If we have a temperature change, is equal to the change in temperature over the change in time. And if I was to write this with delta in it, what does that delta T actually mean? Change in time, but how would I write that out in a formula? When I write delta, I'm doing shorthand. What is delta? If I took out the delta, how would I have to write it? T T2 minus T1, T final minus T initial. You can use 2 and 1 as well. And then time final minus time initial. Oh, great. I picked the example where it's all T's. That won't be confusing in the future. Pressure change. This is only true in a closed system, so the gas cannot escape. Reaction rate is the change in pressure over the change in time. The mass change must be in an open system. Tend to only be useful when you have a gas. Oh yeah, sorry. How high? There we go. Now, as you're writing that, as I went too quickly, just to talk for a moment about your lab as you're getting that down, the lab is quite interesting. It's the iodine clock reaction. It is a timed lab. When it gets to the stoichiometric point, you get a rapid color change. But because the rate changes depending on concentration, you get an effect where as the reaction goes on, the reactants are using up. The reaction actually slows down without the color change because it has to hit the right point. And so you can get an inverse relationship where different concentrations will actually give you not a linear result, but a curved result. And to make it linear, we're going to be taking the reciprocal of some of the pieces. So there'll be some math alterations along before you graph it. Extra Hebden questions are down here at the bottom. One of these is going to have a practice question in which you are using the slope to determine the reaction rate. That is a useful one because that is what you're going to be doing in your lab. Once you have a reaction rate, you want to use the slope and actually to get the actual rate per second.
These have any questions on the sheet you gave us?
No, down here.
No, but like, are they on the paper?
Yes.
We don't actually have the.
No, they're on the paper. Pages 1 to 100 have been posted on the Google Classroom, which is currently, I found out, missing 2 pages, which after we're done this, I'm just going to post there with it so you can see it. I just took a picture.
You have the answer key for it?
As soon as our textbooks come, I maybe could post an answer key. Take a picture as well. Okay, anybody still writing these down?
Why is gas evolves underlined?
If you don't have a gas being evolved, is it going to change mass?
No.
No.
Awesome.
Matter can neither be created nor destroyed. So even though a reaction has happened, if there's no way for any of the stuff to escape, then you're not going to have a change in mass. But if it's an open system and the gas comes off, it should get lighter over time. One of the most experiments that kind of proved this is that a chemist burned something, was able to capture the gas that was given off and also record the mass. And he found out that the mass, even though a gas was being given off, he captured all the gas being given off. He found the mass of the gas given off plus the ashes was greater than it was before. Why would that happen? Why would the mass get larger?
Wrong calculations.
No, he's perfectly right. What is going on when you burn something? What's it reacting with? Oxygen. So oxygen from the air was going in and reacting and then adding itself to the mass. That was one of the fundamental experiments that proved that air was composed of more than one element. He was able to sort out that it was only the oxygen that was reacting. That was one of the elements involved. Anyone still ready? Now we're going to talk about factors that control reaction rates. How can we make reactions go faster? If you want a reaction to go... Theo? Can you put that up there? Oh, that was a phone. What were you playing with on your calculator? You're way too interested in that. I'm now suspicious. That's like 80s level of distraction. We didn't have phones. We only had our calculators. Recognizing some factors that control reaction rates. You want to make a reaction go much, much faster. What's the first thing you could do? Heat it up. Increase the temperature. If the temperature increases, why does that make it go faster? What does increasing the temperature do to the particles? Yep. They will move faster. And they will hit each other with more force. So there's a lot more energy going on, and you increase the number of collisions. So temperature increases. I spelled collisions with 2 I's, apparently. Collisions increase. Therefore, what will happen to the time if you increase the rate of reaction? Decreases. So it's an inverse relationship. If you are running a race and you go faster, your time.
So there's like an end point.
Yeah. And the end point for reaction is when it runs out of reactants. So the faster it goes, the faster it will decrease. About a 10 degrees Celsius increase will double the reaction rate. This is a rough rule of thumb for many reactions. It's not a law, but we have noticed that this is in terms of what things happen. So if you're cooking and you're like, oh, I want this to go twice as fast, I'm at 350, I must turn it up to 700, and then I'll cook it in half the time. That's way, way, way too much heat. Now, there's others involved. Just because you increased it 20 degrees Celsius is about 20 degrees Fahrenheit if you're in freedom units. So if you're at 350, 370 will start to cook it a lot faster. There's also diffusion rates into the food, depending on how thick the food and a bunch of other things. So cooking is a lot more of an art than a science in some ways, because you have to evaluate all of that. But it will double the cooking speed. Now, what else could we do? We did the easy one, temperature. Want thing go faster. How make go faster? Want reaction go faster? Pardon? Pressure increase. If I want this classroom to burn faster, all I have to do is turn on the gas tap, oxygen gas tap, fill this room with oxygen, things go really fast. And I've got a great little, well, I think it's great because I did it. I'm going to show a little illustration of why that works. If you increase the pressure, you're increasing the number of particles, so the collisions again increase, and therefore the time for the reaction decrease. I'm going to draw for this little, there it is. I need a box. Here's my box. There we got a box there. And I'm going to make a littler box there. And let's go for the magic pen.
You have to draw
Version. It's just a box and 4 happy faces. Those represent the happy molecules that are doing your reaction. Now, if I said that this box was, let's say, 2 liters, what is the concentration of happy faces? Yep.
2.
How'd you get that?
4 divided by
4 divided by 2. So 4 happy faces divided by 2 liters equals 2 happy faces per liter. Whereas if I take this box now and shrink it, I increase the pressure. They're hitting the walls more often. Now I have the same 4 atoms in a much smaller space. I've increased the concentration. And so pressure is to gases what concentration is for liquids, which gives us our last one, increase the concentration.
Could you go back?
Yeah. I just wanted to get that in there since I mentioned it.
Wait, pressure is to gases as
Concentration is to liquids or solutions.
If it's half a liter, would there actually be more atoms, or is that just to show that it's more concentrated?
Is there more atoms?
No.
No. This is the show. Even
So
though
it's
you don't
just
have any
to
more
show it's
atoms,
concentrated.
you just made it go more quickly. I mentioned, I think, I don't know if I mentioned this in this class or the other class. I've mentioned they've done studies on once you go to university, who you're more likely to marry, who are you going to form a lifelong bond with. The single most important factor was, I didn't mention it, geography. And not just like, do they go to the same university as you or they take the same classes as you, but the study actually showed if you lived 4 doors down in the same building, you had a noticeably marked less chance of marrying someone than if they only lived 1 or 2 doors down. Just exemplifying that people are just lazy. I could just walk 1 door and then marry that person for the rest of my life, as opposed to, oh my God, to the end of the hallway, too much bother. Concentration and proximity make for reactions. If they are bumping into each other more often, there's more likely for a reaction to occur. So there's not more people. If we spread everybody out, less reactions.
Is there anything for B?
Oh, yes. We jumped to C because someone said pressure. And then I said this leads into, because pressure is just a way of saying concentration for gases, and that leads into the other, which is concentration. And I've got a demo for that. Concentration increases. Collisions increase. Time decreases because I'm getting tired of writing the whole word. Ooh. More collisions because there's more atoms per centimeter, not squared. What is volume? Cubed. And what does 1 centimeter cubed equal in terms of volume? As a reminder from Chem 11, 1 milliliter. So when you hear in a medical show 20 cc's stat, they're just saying milliliter. It's nothing fancy. Hopefully today when I do the demo, it's not as spectacular as in the other class because I showed them 2 different concentrations. And when I theatrically squeezed the bottle of a weak acid, it exploded in my face right there. And I was covered in acid and had to go and wipe off and do a shower afterwards. Today hopefully will happen a lot more safely.
Sorry. Is that voice?
Yep, Mark just going down. It's just plummeting. Although, it is entertaining when the teacher gets injured. Really good elementary school teacher. I still wish that she'd made it through the entire year. She was doing a demo in which she would take this compound that reacted with water, and she would show that you could put it in water and you could take it out again and it would still be ignited. It was phosphorus. And she accidentally, instead of getting the phosphorus, she had gotten I think it was probably potassium, because I didn't know at the time. And so while she's showing us this demo, instead of being lit when she goes in and out of the water, it starts exploding. So then, of course, in her panic to get rid of it, she shoves it down the sink and turns the water on. And then she tries to get it out. And then she runs out of the class. And I'll remember this because some of it had exploded. There's like a trail of smoke behind her as she goes down. It's the greatest thing I've ever witnessed in my entire life as an elementary school student. And she was a wonderful teacher. It was a simple mistake. But she didn't come back for the rest of the year. And I have long thought and wondered what happened to her. I was hoping she came back the next year. So yes, it is sometimes entertaining.
Dude, we should experiment then.
Yeah, no, to be honest, in also retrospect, she's crazy. I wouldn't, like, she got this, I'm willing to do the potassium, the one that she did incorrectly. But the phosphorus underwater, that's like crazy stuff. That stuff doesn't go out. I'd be nervous about it. So, I love this one because this is one that most people don't guess right away because this just says some things are different, so they react differently because it's in their nature. Now, there are some clues with this. There are things that react more quickly and some things that don't react more quickly. I'm going to save this particular one for your lab so you can actually see it. So I'm actually not going to demo this. But when you add these, so this is a preview, you get an instant color change. And for this one, you get a slow color change. And your book's going to ask you some questions. Both of these do exactly the same thing. They go from purple to clear. And why do some things go faster than others? Well, if you have something that's ionic, and they just have charges, that can happen fast. They're just moving, no electrons have to move. They're already charged, so they're already really attracted to each other. So neutral molecules are going to be slower than ionic reactions. And also covalent reactions, where you have bond rearrangements. Or you go have an electron transfer where an electron has to jump from one thing to another. Those are going to take much, much longer. And the more of them that have to happen, the slower it's going to be. And sometimes that's just what chemical it is. You can't change it. I remember being at a Pro-D conference. I've told this story more than once, in which I was with a coach. And the coach had athletes coming up because it was a coach from a university. And they had a program where they'd pay for your university if you went to row for them. And this young lady came up and she was like, I'd really like to go to your college. I'm this in rowing at my high school. I've done this, this, and this. I'm really, really interested in your program. And he's like, great, we'd love to have you. You'll have to talk to admissions. We'll get back to you. She gives him her card. He takes her card, thanks her, she leaves, and he takes her card and throws it in the garbage.
What?
Immediately.
Who does?
The coach from that university. And I was like, what are you doing? You were so nice. And she really wants to go there. Isn't this good for your rowing program? Like, why did you just throw it in the garbage? Do you know something about her? He was like, no. The ratio of your lower leg to your upper leg was wrong. And that ratio determines whether you're going to become an Olympic level athlete or just a good athlete. And he was looking for Olympic level athletes. And I'm like, oh, that's depressing. But also maybe someone should tell her before she runs around to all these coaches who are doing that. Sometimes you just have the wrong ratio. You can be really good at something. You're never going to get into that level because it's a matter of physics. Who is it? Michael Phelps? The one who's won more gold medals in swimming than some countries have won in their entire career at all. His arm lengths are different than the average person, which makes him an excellent swimmer. Now, that being said, I also know a student who came here in grade 10, and this boy was asked by every single coach because they just saw him. They're like, you should take rowing. You should take rowing. You should take rowing. Because already they could tell this is going to be perfect. And he's like, no. And he took ODP for his entire career because he doesn't like team sports and he doesn't like to race and he's never going to do that. You need hard work. You need perseverance. But at an Olympic level, you also need to have the right ratios. Poor David Kelch. David Kelch, and this is completely independent, his parents noticed that he was wrong. They sat him down and they said, hey, would you like to be taller? He was like, what? There's an operation. We've done all the research for you. We'll break your legs and put pins in it and slowly expand them so the bone grows, and then you'll be an inch or two taller at the end. And until that moment, he never thought he was short. I was good friends with him. He was in my high school. He was like 5'4", and he was perfectly satisfied with his life until his parents told him he wasn't tall enough. We all took him out that day. Felt really bad.
What is the page 7, number 21?
Oh, those are all Hebdens? Sorry, I'm just moving because it stopped writing. So whenever you see those... Eraser. No, it's still not working. There and there. So those always refer to Hebdens, and those are the next sections you can do. Now, lastly, the ability to meet. Well, there's one that's really obvious that we haven't mentioned yet that makes reactions go faster. Building a fire, how make faster? You can't heat it up. It's going to heat itself up. How make faster go fire? How make faster go fire? More oxygen. We've done concentration. What do you do when you want to start a fire? Well, you got to apply a match. I've got a big log, and I put a match on it. Match goes out. Log didn't light. What else do?
Covered in Vaseline.
Get a whole different, that's nature reactants, get a whole different chemical. Boom. Also, gasoline explodes in the vapor, so not the best idea in the world. But it definitely will catch on fire and probably a few other things as well. But you just have the log. What else do? Pardon? You have a light. That's fine. What are you good? How many of you have ever built a fire before? Pardon?
Smaller logs.
Smaller logs. How do you start a fire? Kindling, paper, stuff with lots of surface area, stuff that the flame can get to and light on fire. If you have something that has a big log, is not going to light on fire very well. If you have paper, if you have kindling, if you have any sort of fire starter, you can get that going a lot quicker. So this particular one is surface area. And other sorts of phase considerations. So if you're a solid, surface area is important. If you're a liquid, it's not. You're already ground up as fine as you can be. So it's not going to matter. But this is mostly going to matter, and that's why we say phase considerations. Because this only matters if you're a solid. AKA surface area. That's an A there.
What do you mean by AKA surface area? When you said surface area?
Hold it. Yeah.
What are phase considerations?
What does that say?
Which one?
The greater the surface area, the faster the reaction, which I just realized I already wrote there, so I was channeling that. We see this everywhere. We see this in our brains. Our brains have to fit into a small space. So how did we get greater surface area so we think faster? Pardon? The brain, last word? Wrinkles. Sorry, I've got a bit of a clog, so I'm a little deaf in my right ear. So I'm saying pardon me a lot. So yeah, your brain wrinkles gives you more surface area. Who said Mr. Newfield? Yeah.
What's the
greater.
What is
It's the
why
same
is
thing that's
phase
written.
highlighted?
It's the same thing that's there.
What are phase considerations?
Oh.
Why is phase highlighted?
Does the phase matter if you're a liquid?
No.
No. If you're a liquid, you're already ground up. However, if you're a liquid and a solid, it will go faster if that solid is ground up.
Only matters if it's a solid.
Only matters if it's a solid or other things. So what kind of liquids would it matter?
So are you talking like phase? Or are you talking about like the different
Solid,
sizes?
liquid, gas. Yeah, it could be.
Oh.
So what other phases might it matter?
Gas.
In what sense? No, gases would be good. What if you have a liquid and a gas? How could you make the reaction go faster? Yeah. Anybody ever had a fish tank? Okay. How do you make sure that your fishes get enough oxygen? Bubbler. You need small little particles of gas so the oxygen actually diffuses through. If you have that low surface area just on top, not enough gas is going to get in. So you're worried about surface area considerations. So frothing the gas into the liquid is going to be important. If you have two liquids that are immiscible, they are like oil and water, they're not going to react very fast unless you do something to get that surface area there. There's a new TikTok trend I saw in which people are taking ice in their fast food joint that they work at and deep frying it. Why is that a spectacularly bad idea?
Because it makes it deep fry like
Overfill, and if you're really unlucky, explode. The temperature of the deep fryer is much higher than the boiling point of water. The ice melts and then boils in the oil. When it turns to steam, it ejects the oil, and now you have vaporized oil surrounding you. If there is any spark, you now have an explosion.
So then why do they do it?
Because it's on TikTok.
No. Okay.
Yeah, there's no good reason. It's just they wanted to film something.
So what happens? So it just explodes?
Explodes, or if you're very lucky and it doesn't explode, it just the water boils up and takes all the oil and just throws it all over the floor.
But what's the point of doing it? Nothing happens if the water just dissolves. It's like watching a cube melt.
Oh, I have no don't ask me why people post things. People just post things. That's a whole level of psychology.
throws the chicken into the deep fryer and it explodes.
This is also, if you are working on a stove and it's a gas stove and it's got flame to it, or even if it's just hot enough, if you have some oil that's been sitting there, it's been heating up, you throw in some cold vegetables that have been like drenched in water, that can vaporize the oil and you can get a fire right on top of your pan right there and get a little fireball going. What's the safest thing to do at that point? If you're on fire, yes. How do you stop a kitchen fire? Did someone say with alcohol?
Yes.
No.
That's
No.
what it is.
Alcohol will burn. What?
With the fire extinguisher.
Something powdery? A lid? So anything that will cover the flame. What don't you throw on a fire, on top of a stove in your kitchen? Water. Because if it's an oil, that water will just turn into steam and explode the oil all over your kitchen. And now a pan fire is now a whole kitchen fire.
Have you ever left the oven on and started baking some beans and then lit a candle?
No. That sounds like a very bad idea. Anyway. Yeah. This is just a side of what is the fastest type of reaction, what is the slowest. I think I spelled fastest there with an A, that should be an E. So the fastest are the things with charges that don't have to move electrons around, so aqueous ions. Tied for second place are gases and liquids. Gases, particles move faster, but they're also further apart. Liquid particles are moving slower, but they're also closer together, so they can be 6 of one, half a dozen of the other. And slowest of all are solids. You're going to get another list that's going to look very similar to this for something else. Don't confuse the two.
Alan wants to be gotcha, but who wants to?
Oh, I didn't ask a question. Anybody still not done? Solids. What are the particles doing in a solid? You said moving. Then was that stationary, not moving.
Will they vibrate?
Do not move. They do vibrate.
It already says do not move.
Yeah.
The solid particles or molecules then do not move. The only thing that's exposed is the surface area. And that's the only spot that can react. If you have liquids and gases, then this is an everything everywhere all at once type of situation. Every molecule is available. They're also moving at high speed. And in liquid, we have close proximity. They're all available all at once and they're right beside each other. Unlike a solid in which you have essentially only the outside, everything is protected inside and you'd have to grind it up to get it. Aqueous ions have the huge advantage of liquids. They're being close together. And what kind of attraction is positive and negative? The fancy word for positive and negative attraction. It is an ionic attraction, but I'm looking for the general term. Pardon? Close to electromagnetic. It's electro...
Negativity.
No. They're not all negative. Electrostatic. Electrostatic just means positives and negatives attract. It's a fancy word. Now, the last way to get reactions to go faster is just adding another chemical that makes it go faster. That's called a catalyst. We're going to do a little bit more work with catalysts later. They have a specific mechanism by which they do that. It's defined, a chemical which increases the rate of reaction but does not change in the reaction. And I'm going to put in red because we're going to learn this later, but as a preview, red. Red lowers the activation energy. But does not, but does not change in the reaction.
Could you read off this?
Did this partially erase or something?
Yeah, you actually erased it.
So, a chemical which increases the rate of reaction but does not change in the reaction. I'm hopefully going to have time to bring out some hydrogen peroxide. And that very slowly at room temperatures decomposes to oxygen and water. So slowly, you would have to wait a couple of weeks. It will slowly go. Eventually, the hydrogen peroxide we have in the lab goes bad. It's just that it's all fully reacted and has become water.
So after which?
But if we want to make it go faster, we just need a volunteer. Yes?
How can a chemical not change in a reaction? Like, what do you mean not change?
It itself is not reacting, but often what it does is it offers a new reaction pathway. So often a reactant will attach to it, and that makes it easier for the reactant to react, and then it just detaches. And so the chemical is left over.
So if it was written out, it would say the same level.
We often will write it out. I'm going to put it here, but if we were to write it out, A goes to B and C is a catalyst, we'll often put it here because it would be plus C and plus C. It wouldn't change.
So it'd be like adding pressure to it.
No, that's changing the concentration. If I have a volunteer for the next one, all I need is some liver enzymes.
Yeah, Andrew actually.
Excellent.
What you said, you want to give him Oh, yeah. I love to hear.
It's like the next.
Occasionally, when the biologists are doing a dissection, I'll borrow some liver, and I can show you that it really works quite well. If you don't have liver enzymes, manganese dioxide also works reasonably well. And you can get it to decompose quite quickly. And then you can just boil off the leftover water, and you get your manganese dioxide back. It's completely unchanged. It just provides a new pathway for the reaction that's just much quicker than normal.
So like, how was it used? Was it like say it's conducting electricity, or like that sort of way? Like, how is it used but not used?
The reactant will attach to it in such a way that the reactant can now react faster. So it just bumps in the right way. So it positions it. Pardon?
It attaches to it.
It attaches to it often. Yeah.
Like a
I
battery.
think both said
Like a what?
Like a battery.
Not a
So,
battery.
Like, it gives
It
more
doesn't. It doesn't provide energy. It's like it provides a shortcut.
But what is that shortcut?
We'll do this when we do reaction rates and catalysts a little later on. But if you were, say, putting, I don't know, piece of paper into binders, so you're filling a bunch of binders with 50 sheets each. A catalyst would be something like just a piece of machine that you line the papers up with so they're perfectly aligned, then you put it in. It'd be faster than one at a time. So so often what it'll do, it'll attach to it, but it'll attach to it in a way that exposes it so that when it hits something, it's more likely to react.
So like flattens it.
Maybe. It depends on the specific reaction. Yeah. I don't want to give specifics because there's so many different ways you can do it. Does anybody know what an inhibitor is called if you eat it? An inhibitor.
Like during
Something that kills your enzymes.
yeah, like the inhibit like stop production.
Yeah.
You eat it.
If you eat it. And it stops your enzymes. It's called a
Blood clot.
poison. I think I misspelled poison. It's an O, isn't it? That looked wrong. There we go. Antibiotics literally mean anti-life. They're all poisons. But they poison your ability to make a cell wall. Since bacteria make cell walls and you don't, it tends not to harm you as much. Although you have more bacterial cells in your digestive system than you actually have human cells in your entire body. So it can have a lot of effects because you're killing off the good bacteria as well as the bad. Antibiotics are just essentially chemotherapy for bacteria. This reduces the reaction rate by combining with a catalyst or a reactant to prevent reactions. There is a mushroom on Vancouver Island, not the one you're thinking of. It actually binds to your ribosomes and it stops all of your ribosomes from working. What effect would that have on your body?
Can't reproduce cells.
You can't reproduce cells. What do ribosomes do?
Protein.
They make proteins. So they make every single enzyme in your body. If they're not working and you eat this mushroom, and we know the mushroom actually tastes good. It's got a bit of a nutty flavor. Apparently it's really good with onions because you can talk to these people who have eaten it for like 3 whole days. But as their ribosomes wear out and they can't make new ones and they can't make any new enzymes at all their cells start dying at the same time, roughly. And so all the pain centers in their body go, hey, there's a problem here. Your cells are dying. But since your body can't fix anything, it just gets worse and worse and worse. The only treatment is to put them into a coma. And the treatment is mostly for everybody else because you die after you're put into a coma. It's just to stop you from screaming so that everybody else in the hospital can like get along. So if you eat wild mushrooms, you should be with someone that knows absolutely what it is you're eating. A trained mycologist is someone who's been out there, who knows what mushrooms are edible and not edible. If you make the wrong mistake, mushrooms are one of those species or groups that can be incredibly poisonous. There's also other types of milder poisonous ones, but there's a few that are really deadly. I think this is the last page. Sorry, and I moved on without asking. Anybody not done? More Hebden down here.
Is this all due, like all what's all the due?
Oh, I will take in your Hebden and look at it, like when you write a test, or randomly throughout the year. So you are working on it a little bit every night.
Do we have to do everything that's on there, or just parts of it?
I'm going to post an Excel spreadsheet, but it hasn't been very much so far, so I haven't posted that yet because we've just been doing these
No,
little
I'm saying
bits.
if we read through it and we understand it, and we think like it
Oh,
would
there's a
make sense.
minute. Yeah, you do have to do these.
Also, we actually have to have
Yeah,
this
you
done.
have to have. Yeah. What does homogeneous mean?
One.
One thing. One, and genius, phase. So homogeneous in this particular case means that everything's in the same phase. So we're talking gas, gas, aqueous, aqueous, liquid, liquid. Why is there no solid, solid listed there? There's no solids react incredibly slow. Are two solids mixed together in the same phase? No, they're both solids, but they're not mixing, so they're actually different phases. You can't get, you'd have to grind them up. They're considered a heterogeneous type of phase because you have to actually get them to mix. Whereas if you just take two liquids and pour them into each other and they mix, they're considered in the same phase. Everything's in close proximity. And these are fairly rapid reactions. And these don't consider surface area.
What is the?
There was no SA. So.
Surface area. Yeah, I just realized in the last 5 years, SA has come to mean something completely different. So I should probably write out the whole word. Now, if you have homogeneous reactions, then you would also have heterogeneous. These reactions are in different phases. And we can have solid, liquid, liquid gas, and that would be bubbling through for your poor little fishies. But there are cases in which you have liquid, liquid. Now, I haven't listed all the different types because, of course, you could have solid gas, and I don't think I put there. In what way could liquid-liquid reactions be in different phases? Yep. Water and oil. So if there's a fancy word for that, and that is immiscible. Were you about to say it? Sorry.
No, it was something different.
Two M's.
2 M's. IMMISCIBLE. Immiscible means doesn't mix. So oil and water.
Would viscosity also be up there or no?
No, I haven't heard of that. As long as they both mix. Now, their viscosity may affect their rate of reaction because the slower a liquid moves, the slower it is. But as long as they can mix, it would be considered the same phase. It'd still be more rapid than something that was immiscible. Yeah. But that's a factor that could definitely affect it.
Wait, so reactions that don't mix can't react, or
They can react. They just don't react quickly. And these are the ones that are affected by surface area. I'm going to try, without having it blow up in my face, show you zinc in sulfuric or hydrochloric acid. And we'll do it in both chunks of zinc and in very fine powder. Burning a log versus burning splinters. There's a bit more Hebden there. And if you have access to Mythbusters, we may show that in class if we have time at some point. They do a fantastic example of this. Now, thank you for that. I know that was a long class of notes. I don't know how it happened. We actually got a little bit behind the other class, so now we're completely caught up. I want to make sure we're ready to go for our lab. This is a assigned reading, page 10, examples A to G. And this is just a summary. These are all the Hebden questions that we've been assigned so far.
The reading is from where?
Page 10, examples A to G.
Where?
Is that the third book?
Do you have the handout? The Hebden handout?
Yeah.
Oh, it's in there.
So that's Hebden.
Yeah, it's Hebden.
So that's
When-
just assigned reading for next month.
Yeah, unless I say otherwise, all page numbers refer to Hebden. The big thick text you have is solely for backup purposes, and if we discuss something that's not in Hebden, and the other one's just for labs. Good point. Now, if you want to start on your pre-lab, you can start on some Hebden. I'm going to grab some examples and bring them up. In the last 15 minutes of class. And hopefully today, I'm going to load into my face.
Oh my god. How are we doing the pre-labs? We're like how our commission's not being affected. I don't know what reaction it takes to
What?
Bro. This close. 300 bucks, bro. Plug mine.
They're just sitting back and
It would have been what? 20? Oh, wait, what were you at for? So one is 1.9 and then it's 3.8. Or 17, and then
I tried to. He answered like
102, and then
I'm like 277. So six lines? 600.
no 500 for 500.
No, but I got two lines.
I don't know,
even
two times two times five. And then
Yep.
A single person or like a group thing?
You'll do it in pairs, but you write it up individually. KClO3. We're going to start with our surface area considerations there. Also,
That is not what it is.
For that, Mr. Nichols, for that, do we need to like answer that question? Like discuss the situation?
repeat 10A, the examples.
But do we need to like discuss discuss situations in which if the reaction needs to be controlled there.
Yeah. Oh, you don't have to write anything down. As long as you read through the examples or understand what's going on, you're good.
Luke, what is the next test?
Once we're done, we just finished A. Once we're done B and C, we'll have our first test.
Will there be?
Will there be what?
We're starting B. That's a lot.
Okay, I have a demo close to getting ready to go. There's another class out there, so we're gonna have to like whip out, watch the fume hood, and then kind of whip back in. So I want to set it up in here a little bit. I have this plate. This plate is potassium chlorate and table sugar. So the regular sugar you would make when you make any cake. It's got that crystal size that you've seen before, I'm assuming. And here we have potassium chlorate and white powder and icing sugar. Which one would we predict should go faster? Why?
Because sugar reacts.
Well, I've got sugar in both.
Oh,
You just said sugar
well,
reacts.
ice is like.
What?
Ice is like.
Ice?
Yeah, you said icing sugar, right?
Yeah.
Oh,
What is icing sugar?
no, never mind.
It's more what? It's porous? I don't know about porous. I don't know if
It's
that's quite the right. Is what?
Fine.
It's finer. Okay. Ooh, I might have added too much icing sugar. Hopefully this happens properly.
The same one, mine's just black. Actually, this is translation. Yeah, accepted by every school in university. Or every university in America. They're like,
Now I really want to get
no, for real. The questions are like, bro, whenever you do this, yeah, no, you can't place that anymore now. You can't say you're white. You have to say undefined, because if you say you're white, then you're going to accept you. It's just how it is.
What if it was just me and Anna?
So say you don't know.
I'm gonna ask him
And I'll be like, God, we can find out. We should accept it.
Get scared.
Pulling up the weather app.
It's like, oh my God, Jordan, that's green. So, like,
I just can't. Oh, you question. If I do, I catch like one, but if I do a full, like, you
Yeah.
can't go 5 times 12.
whatever number you can't win, anything.
Okay. Miss Chung is giving me permission to use the fume hood while she's using the lab. Please be a good guest. Whip in. Look where you can see the fume hood. I'll do both demos, and then when you've seen them both, we're going to come back in. Don't interfere with them while they're doing the lab.
You buy
I
them.
have a 16% chance to get this.
You do look like great.
Like, I edited mine. Like, I photoshopped it. No. If he got all 5, he would have been.
That's tough.
Yeah, I'm gonna keep going.
Give me my fucking nerve.
This is what I'm talking about. How? I'm not even joking. I think I just did it by accident. And I swear it's like in the millions.
Dude, if we got $5 million in tech, that's like fucking.
We're home break over at us. Oh, like, yeah. No, wait, what's this? Oh, no, I haven't had
But
it.
if we get the full board in the game, we get $5 million. We should just do 10 cents.
No, yeah, like, it's our graduation requirement.
Oh my god.
Well, that means my next semester you'll see. It's always second best. Yeah, we have to. I have
Yeah, for like I represent
If I'm away and I'm working getting demos, you are working. You're working on your Hebden, you're working on your lab, you're not on websites. Put your laptop away if you're not using it for anything chemistry related.
What is Asper? The right's the one.
This class is in the kitchen.
What's your team?
Have you lost all your points yet? Huh? Have you lost all your points yet?
I did.
Sorry?
It's like pretty good.
No. The way I fight people is with like
Dude, we're gonna meant to do 13 diamonds with all mine. If we get all the diamonds, it's 5 million.
What?
Earlier we got 206.
That was so bad.
Yeah.
My writing is
Dude, if we do 1 cent, we get
all day, every
$50,000.
1 cent bet, and we
50 grand, bro.
50
grand.
Aren't these supposed to have good writing? That's crazy.
Bro, 1 cent times 5 million.
The subject that they teach
You know, but
in grade 9, they both failed.
what is the chances of that?
What are the chances of getting it?
Ms. Winsky passed math 9 and 59.
Skill.
So I do pass looking 60
It's 1 cent.
57.
Putting 1 cent.
Still
Where's the pre? Oh yeah, Mr. Bell. How are we supposed to do the pre-lab?
You were emailed the pre-lab. What do you mean? I'm not sure what you mean.
It's on 2 o'clock.
And it was also emailed to you.
Actually,
And you have your lab book.
So just read the lab book and then
It's lab ATB. Go to the lab book, go answer the questions, and make up a flow chart. Yep.
Wait, we have to do the questions in the lab.
Yep. No, I've given you questions to do about the lab book.
So like, when we read the lab, these are questions in the lab.
Yeah, they require you to understand the lab.
Where do you put the questions? In the headed book?
No, you print out a piece of paper.
Bro,
You print out a piece of
I
paper.
don't remember this, but apparently when I was like 4 years old, I bit into
Check your email. I had 2 of those. Where's the other ones?
It's in your laptop. It's in like that.
Yeah, my mom keeps bringing
No. I had 2. There it is.
Gee, that's my mom's so low.
Why do you live there? We put in the south.
No.
It's getting hot yet? Close enough.
Do you sit this slow all the time? Oh, I'm guessing like the cold water version.
Yeah.
You said
That's the hot water.
Before you go, please have a seat. Chemistry 12, sometimes we take longer than 115. So we see a difference in, now this was in there for a couple of minutes, so it shouldn't be slowing down. This will just take a second. We can already see that there's a little bit of a light difference between the two. And so that is the demo in terms of how temperature changes the rate of reaction. If you want your glow sticks to last longer, put them in the freezer, they'll still be glowing the next day. But if it's a hot night, they won't last nearly as long. Okay, now you can go. Thank you very much.
Thank you so much for this amazing class.
You're welcome.
Yeah.
That's it. Next day's demo, lab, make sure you come with your lab sheet done.
If we make anything over a grand, that would be counted.
That's why you're just waiting.
Oh, if we could finish over $200, I'm happy.
Class for people who like commit.
We bought 50 grand now. Like, we gotta figure out how we can.
Yeah, well, you have to do the quiz, so I do it if you want to promote, and then bring library prep. I think they're starting library prep now, they hadn't been before. Well, library prep is anything. Yeah, but there's like test prep at night in like, that they hold it, that's not starting until next week. Library is like you go to the library during a spare block, and you can just write a test in the library. Like, what's your spare?
My spare is
C-block, so you can just go there during C-block and write. Now, I haven't put it in yet. If you email me that, I'll make sure it's there for you, and then we can get it done.
perfect. Thank you.
Thank you.
Alright, here's my question for you. Probably simply answered. So this one, copper, solid, it asks in the next question, which of these reactions are homogeneous?
Right,
This one is not.
right.
Can you elaborate on
Because,
that?
for the
Like-
same reason that two immiscible liquids are not homogeneous, because they don't actually mix.
Okay,
So heterogeneous refers to the fact, homogeneous refers to the fact that like the molecules themselves are mixing,
yeah,
so two solids can't mix.
yeah,
So there may be two solids there, but they're not moving into each other's phases.
okay,
So two immiscible liquids are also not homogeneous.
okay. Cause it says, in its example, oh, this is where, cause the note says, not homogeneous because Cu and S are different solid phases.
Yeah.
Okay,
For them to be, I think technically for them to be homogeneous, they'd have to be in the same solid phase. Like
Okay.
they both have to be part of the same solid,
in
Which-
order for it to be, okay,
which doesn't really happen with solids.
okay. That makes sense. Solid phase are, homogeneous.
I'm gonna clean up at the same time just because I do have a meeting